welcome Dr. Kanwal.
Thank you. Thank you very much. So first of all, I just want to let you know that it's a real pleasure for me to get an opportunity to speak in the place where more than 50 years ago I got my inspiration to do physics. And I got it because of some of the great teachers that we had here and the persons that we got to listen to. So I hope that some of you sitting here in the audience today might see something that gets your attention today and maybe makes you want to study the subject of physics. In any case, welcome and thank you for coming. And I will ask that you leave your questions towards the end, but I will try and make some time at the end for any questions that you have about the talk. So the topic that I have today is cosmic microwave background radiation. So just to get a little bit of an idea about my audience today, how many of you have actually heard this term before, cosmic microwave background radiation? Oh, okay, a lot of you. By the way, how many of you are studying physics in IT? Oh, a lot of you as well. So this particular discovery was made in New Jersey, in fact, not too far from where I live there. And it was made by an instrument that is called the horn antenna. And I'll show you some pictures of that. How many of you actually know what a horn antenna is or have heard about it? Not too many people. Okay. So you will learn a lot about the horn antenna today, and that's what I'll be talking about. So I'm basically going to tell you a story today about how this detection happened and give you some idea about the significance of this discovery. In my view, the discovery of the cosmic microwave background radiation is perhaps the greatest discovery that has ever been made in physics for sure, and maybe even in science. I will tell you why I think that this is such an incredible discovery. So first of all, there have been lots of amazing revolutionary discoveries in physics. I'm sure those of you who are studying physics have come across some of them. I have a list of them here that I'm going to quickly go over, and then I will tell you why this discovery, which is essentially about the origin of our universe, why this discovery in many ways is the most amazing thing that has happened in physics. So here is the list of some of the most incredible discoveries. Perhaps the first discovery in science was the very fact that we can do science, which means that there is an order in the universe that we can study and use to explain what is going on. For a long time, thousands of years, people never thought that there was any order. Everything looked very chaotic. So that is an incredible change in perspective. Then another big thing that happened was that Copernicus showed us that the Earth is not at the center of the universe. It is actually just another planet going around the sun. And that discovery completely changed the perspective that we have on the universe. We were no longer being the center of everything. We were just part of a much bigger thing that was going on. Then we found out that the laws that run the universe are the same everywhere and for all time. So one of the discoveries was that those laws that work on the surface of the earth are the same laws that work in space everywhere. Before that, people used to believe that the heavens are run with the different kinds of laws, and we have a different set of laws here. So that was an incredible change in perspective. Then we had the discovery that everything is made up of atoms. The idea of atoms was started a long time ago by the Greeks, but it was only a few hundred years ago that we found out that we can take 100 or so atoms and use that to make every single thing in the universe. And then we have some of the more recent discoveries where Einstein found out that space and time are not universal. So my space, it may not be the same as your space, my time may not be the same as your time. Space and time are relative, and that was the theory of special relativity that Einstein came up with. Then again, after a few years, Einstein came up with yet another theory, which we call the general theory of relativity, which shows that what we thought was a force of gravity is not really a force at all. It is actually space and time curving together to create a situation that makes us think that there is a gravitational force. And finally, coming even closer, the latest discovery has been the discovery of quantum physics, where we now understand that even reality is something that is created by the person that is observing the reality. And so it is our observations that actually create what reality that we see. So these are all incredible discoveries. But the fact that the universe has an origin is a unique discovery, because it not only changes our perspective on the universe, but it actually suggests a new role for science. Up until now, science was supposed to simply explain how things work. Now, science has been able to tell us that there was an origin, that there is a source from which everything in this universe has evolved. And that allows us to ask questions that we could never have imagined asking. We can now ask the questions, what is our relationship to that source from which everything came? You can ask the question, the fact that we are part of an evolutionary history, a 14 billion year evolution history, does that give us some new meaning to who we are and what we are supposed to do? These are questions that were only asked in the past in a religious context. Now we can ask these questions using science. And that is an incredible change. And that is why I think that this particular discovery is really something very, very big and amazing, which we are still in the process of digesting and figuring out what it means for us. So to kind of give you an idea how the background of the fact that there is an origin of the universe, it actually comes from something that is very inherent in us human beings. For thousands of years, we have always created, even when we do not understand science, we have always created a myth about how the universe was created. There is not a culture on the face of this planet that did not have a creation myth, a myth in terms of how the universe was created. Those myths are mostly supernatural. They assume the existence of gods, of deities, of all sorts of things. And they were put there not just for entertainment, not just so that people can tell stories. Those creation myths were put there to bind people together, to make them come together under a common belief. And they were also put there to give messages to people about what they should be doing in their life, what is good, what's not good, how they should live their lives. So all of those meanings were inherent in those ancient myths. And it is these ancient myths, as they evolved, they became what we now call our religions. So the institutionalized religions that we have are really an outgrowth of those ancient myths. So the question then arises, how does science jive with these creation myths? And that is the story that I'm going to be telling you today. So in the beginning, when science, official real science didn't start until about 400 years ago, even though the Greeks had come up with some ideas, but that was not true science. True science started with Copernicus, Galileo, Newton, and so on. And in the beginning, religion and science were not at a conflict with each other. They were sort of partners. Most of the original scientists, like Newton, like Copernicus, they were all religious people. They believed in the Christian religion, which is what they were a part of. But over a period of time, it became obvious that religion and science were in contradiction to each other. So at that point, it became important to distinguish what is science and what is religion. As a matter of fact, Galileo, who claimed that the earth moves around the sun, was put under house arrest, and his books were banned by the Christian church because they felt that it contradicted the doctrine of Christianity, which was based on the earth being at the center of the universe. So as time went on, it became very obvious that religion could not continue to deny what science was discovering. And so what happened is that they basically kind of made a little bit of separate ground for each other, where science was supposed to do some things and religion was supposed to do something else. And so this was some kind of a truce that came between religion and science, where scientists felt that their job was simply to tell how the universe works. And the religion job was to talk about the creation of the universe and other things that are associated with that creation, like giving meaning and purpose to life. But the problem with religion is that once religion has certain ideas, it fixes on them. It does not evolve. It is rigid. Science, on the other hand, evolves over time as things change. And so this truce was bound to get broken. And indeed, it did get broken. In the 19th century, it became very clear that the biblical story of creation could not be held under the microscope of science. Science was beginning to find out, well, first of all, as many of you I'm sure are aware, the biblical story of Genesis basically says that the universe was created in over 7 days or 6 days. And in fact, it gives a time frame for when it was created. And if you study all sorts of historical records, you can basically come up with an age of the universe that is about 6,000 years. Now, it was becoming very obvious that if Darwinian evolution was going to be true, that could only happen over millions of years. It also became obvious that the thing that forms mountains and geological things also happens over millions of years as different kinds of rocks settle down in the ocean and create layers which then get exposed. So it was becoming very obvious that there is no way that the Earth could be, or even the universe could be 6,000 years old. Interestingly, I just wanted to give you a little fact here. By putting all sorts of data together, there was one Christian person who came up with an exact date for the creation of the universe. And this is actually, it's in the King James Bible. I don't know whether they use this version now or not, but it actually said the universe was created at 6 p.m. on Saturday, 4004 BC. Anyway, this could not hold under what was going on, and therefore it became necessary for science to take on yet another kind of a role that kept it away from religion at that particular time, which was mostly Christianity in the Western world. So the interesting thing here is that we associate all of this mythology and dogma and so on with religion. But if you look carefully, you will find that science has its own myths and its own dogmas. And in this particular case, one such myth developed as a way of keeping Christianity and science separate from each other. And that myth was this idea that the universe never changes. The universe always stays static. And so the universe science did not have at that point any way to talk about how the universe was created. There was no such thing. So what they did was they said that the universe has existed for all time. And yes, the biblical versions may have some ideas about how the universe was created, but those don't interfere with the science, because in science we just assume that the universe is there and we look to see how the universe was. So the eternal universe became an idea that took force in the scientific community to the extent that even though there was no evidence for it, it became something that all scientists believed in. And so the rest of the story that I'm going to tell you is not about a story between religion and science. It is a story between science and science. It is the story about how science develops and how science has to fight against its own establishment in order to make sure that new ideas can be accepted. And you will see in the story that it's not easy. As a matter of fact, we have to admit, of course, that scientists are also human beings. So they have their own, issues that come with being a human, and part of that are things like, jealousy, ambition, all sorts of things that happen. And so in this story, you will see that all of those things play some kind of a part. So the story here does start with Einstein, and Einstein, as it turned out, became the first person to challenge the myth of eternal universe. The funny thing is that it came to Einstein not as something that was a huge discovery, it came to Einstein as a disappointment. And this is because Einstein, even though he was such a maverick in so many different ways, Einstein had bought into the myth of science, which is to say that the universe is eternal. So when his equations, his equations of gravity can be applied to the whole universe. That's what he realized in 1917, a couple of years after he had put forth the theory of general relativity. And when he applied that theory to the whole universe, something interesting came out, and that was that the universe had to be dynamic. It could not be static. It could not sit in one place. And in his way of thinking, the way that it turned out for Einstein was that the universe would collapse. That was not something that he wanted to tell the world, that the universe was collapsing, and he himself didn't feel comfortable with it. So he did something that we now call a fudge factor. He put in a new part of his equation, which is called the cosmological constant. And it turns out that by putting this cosmological constant, you do not change the results of all his theories in terms of how gravity works. But what it does is it creates an anti-gravity force in the universe in such a way that that anti-gravity force can balance the gravitational force that is collapsing the universe. And by doing that, he was able to create an equation which would support the idea of an eternal universe. He was not very happy about it because this made his equation not look as elegant as it was before. But lots of physicists and so on were happy that he could come up with some way in which it could be consistent with what they thought the world was like. And so it was reasonably well accepted. Most of the time when these things happen in science, it is the people who are separate from the establishment, those who are not part of the mainstream science, who come up with new ideas that challenge the establishment. In this particular case, it was a Russian physicist, a very young Russian physicist. And at that time, this was the time that the First World War was getting started, and Russia was rather separated out. It was isolated. And so it was also isolated from the ideas of the establishment. So this young man by the name of Alexander Friedman did not accept the idea of putting a cosmological constant. And when he did not put the cosmological constant, he was able to take Einstein's equations and actually solve them mathematically to find out what the result of those equations would be. Einstein himself had not done that because he had come to this cosmological constant, and that stopped everything for him. So Alexander Friedman found out that if you take his equations, you get three different kinds of universes that you can then characterize. one of those universes will be one that will continue to expand forever. Another one will expand, but then it will sort of, level off and kind of just keep expanding at a constant rate. And then the third one here was the one that's called the closed finite universe, where it would first expand, it would reach a maximum, and then it would start contracting again. So this was an idea that had not come up yet, that we could actually be living in an expanding universe which had been kick-started at some point, and at some point it might come to a maximum and then collapse again. So this was a new idea that he had introduced. But once again, because he was a Russian physicist and because he was isolated from the mainstream, his ideas did not gain much momentum. Einstein, of course, knew about the work, and Einstein criticized it. He said that this is fine mathematics, but it doesn't really apply to our world. And when a person of the caliber of Einstein criticizes something, that makes it very difficult for anything to move further. So Alexander Friedman's work was mostly forgotten until another person with a very different kind of a background came to the fore and revived this idea and revived it in a new way. Also, Friedman was a mathematician. He was not so much of a physicist, so he did not carry this thing any further than these ideas. So this new gentleman that appeared was a Belgian physicist, Georges Lemaitre, and he has an interesting history. He studied physics, he got a PhD in physics, and right after that, he joined the seminary and became a priest. So one of the things that he says about him is, he said, I think that there are two ways to search for truth. And I decided to follow both of them. So that's what he came up. Anyway, Lemaitre is actually credited with the idea of first proposing the Big Bang Theory. He did not call it the Big Bang Theory. In fact, the Big Bang Theory name came much, much later. But what he said was that and he actually recalculated all of Einstein's equations. He did not even know about Friedman's work. And he discovered that if we live in an expanding universe, then you can make the clock go backwards. And therefore, if you keep going backward, you come to a point where the universe was very tiny. And this idea led him to believe that our universe may have started out with some kind of an explosion. He called it the primeval atom, because he, at that time, was we were starting to understand the idea of radioactive decay. And he said that maybe there was some kind of an atom in the beginning that decayed and then started to expand and led to the universe. Once again, Einstein criticized this. In fact, his words were, your math may be correct, but your physics is abominable. And so in the beginning, his work was also not very well accepted, but he continued on. And one of the predictions that he made was that if the universe is expanding, then when we observe objects in the universe, mostly galaxies, in fact, at that time, it wasn't clear whether what were called galaxies were inside our own galaxy or whether they were outside the galaxy. That was something that came later. But whatever objects exist in the universe, they would all be moving away from each other if the space between them is expanding. And so if we look at those objects from the Earth, we will find all of them moving away, and the ones that are further away will move at a higher speed. The best way to sort of look at this analogy is to think about a cake that has raisins inside it, and as the cake expands, all the raisins get further and further away from each other. So no matter which raisin you are sitting on, you will always see the other raisins going further and further away. And so that was his prediction. And interestingly, our telescope technology was advancing very rapidly at that time, and within a few years, his prediction was actually verified by a man called Edwin Hubble. Well, before that, let me explain to you that this idea about figuring out whether or not the objects in the universe are moving away faster and faster the more further you go, implies that we have to have a way of first knowing how far these objects are, which is not easy, and secondly, to measure the speed of how fast these objects are moving away from us. That required new discoveries, which luckily were being made in the same time frame that he was predicting what would happen. So the first discovery that I'm mentioned here is from Westhoff Slipher, who actually found out that by using red shifts, and I won't go into the physics of this, it's called the Doppler effect. By looking at the red shifts inside the galaxies, you can actually tell how fast they are receding away from us. The other thing that was very important was to figure out how far these galaxies are. And that research was carried out by a woman astronomer that is unfortunately did not get the recognition that she deserved. But she was the one that created a relationship called the period luminosity relationship, where she showed that there are certain kinds of stars that vary in size from being brighter and dimmer and brighter and dimmer. And by looking at how quickly they go bright, dim, you can actually calculate the true luminosity, the true brightness of those stars. If you know their true brightness, and if you also know their apparent brightness because of how bright they look when you look at them, you can take those measures, two measures, put them together, and you can actually figure out how far they are. You know, just like by looking at the headlight of a car, you can get an idea about how far that car is. Similarly, you can do that with stars as well. So that discovery was very huge. And with those two discoveries, equipped with that, Edwin Hubble, as I mentioned, in 1924, he first found out that all the little nebula that we see in our galaxy, which were like swirling, gas clouds, that they were not, many of them were not inside our galaxy, they were actually outside. So he measured the distance between them, and he showed that these are other galaxies, and therefore our universe suddenly, from being one single galaxy with empty space around it, became a universe with thousands of galaxies spread around. So that was a huge discovery. Once he made that discovery, he went on after a couple of years, and he was able to, he was able to then show that relationship that Lemaitre had predicted. And so this was a huge discovery that should have led people to start believing in the Big Bang Theory. But that did not happen. And that did not happen because of some very unfortunate circumstances. And that was that in making these measurements and making these curves, what Edwin Hubble did not know is that he was making some systematic errors. Nothing to do with him. He was doing a great job. But the fact that he had figured out this relationship, it turned out that there were two kinds of variable stars. And he was mixing those two variable stars, unbeknownst to him. And as a result of that, the age of the universe that he calculated, which you can figure out once you know how fast the galaxies are moving, was 1.8 billion years. That was a bit of a disaster because at that time, radioactive dating had shown that the Earth was about 4 or 5 billion years old. So when people saw that, they basically made fun of it. And they said, something is sadly wrong with this theory if the result is coming out so out of whack. So this particular thing should have been the glory of Big Bang, where Big Bang should have been, become of being accepted. But unfortunately, it became the butt of jokes. However, Einstein, credit goes to him finally. He understood that he had made some big mistakes. And this is a real photo with Einstein looking through the telescope and Edwin Hubble in the background. And he admitted in 1933 that he had made a blunder, that the cosmological constant should never have been in his equations. And he started to believe that the universe was indeed expanding. But he became only one of the few people that believed that at that time. So the story becomes much longer. So now we have to keep going to really prove to the world that the Big Bang Theory is true. And in order to do that, there are a few things that the Big Bang model should create evidence for. Of course, the first thing is that if the Big Bang model is valid, then it should be able to show us where the universe came from. After all, the Big Bang is the origin of the universe, so we should be able to figure out why the universe has the composition that it has. Now, it turns out the universe is mostly hydrogen and helium, and a very small 2% of the universe has all the heavier elements in it. So that was the process that needed to happen. And in order to do that, we had to understand what we now consider to be nuclear physics. So major advances in nuclear physics were made in the 1930s and the 1940s. And George Gamow and Ralph Alford actually were able to use that new physics to show that the correct ratio of hydrogen and helium in the universe can be shown to be created in the Big Bang. Once again, that should have been a huge victory for the Big Bang theory. But unfortunately, a whole bunch of other things were happening at that time. For example, one challenge that people gave this was, they said, okay, you've been able to figure out hydrogen and helium, but where did all the other elements come from? Because the Big Bang does not create those other elements. So that again, gave people more criticism to do. But there was one thing that would finally prove to be the breaking point for making the Big Bang theory acceptable to the world, and that is that these same people, Alford along with another guy, Robert Herman, were able to predict something very interesting. They said that if the universe started with a Big Bang, there would be a time as the universe expanded and cooled where all the electrons and the protons would come together and make neutral atoms. And at that temperature, where they make neutral atoms, suddenly all of the light that was trapped in that universe, because it turns out that light is scattered by charged particles. But when those particles combine to make neutral atoms, then the light suddenly gets freed and it can go anywhere that it wants to. And so they predicted that there should be some kind of a radiation that should be permeating our whole universe. And it turns out that with radiation, you can calculate the temperature of radiation. I mean, you know what temperature means for solid bodies, but it turns out that there is a way to define a temperature for radiation as well. And they calculated that this radiation should have a temperature of around 5 degrees Kelvin. Kelvin is basically a measure of temperature from the absolute zero. So this was a huge discovery. If, after this discovery, it should become obvious that the Big Bang theory, if we can find this radiation, there would be no doubt about it. But again, something strange happened. By the way, I just want to show you here that when the universe expands, the radiation that is generated, which is a visible light, also keeps expanding so that the wavelength of the light, which is basically the distance between two peaks, the wavelength of the light keeps increasing. And so at this point, where the universe has expanded to this degree, you can show that the radiation, which was visible light at that time, will now expand to another kind of radiation, which we call microwave. Those are the same microwaves that you use in the microwave oven. And so those microwaves is what we would have to look for if we want to find this radiation. It would not appear to us as visible light. Anyway, so all this was done. So the next thing would have been to build detectors to detect this radiation. But it didn't happen. There's probably multiple reasons, and this issue is still debated in physics as to why did we not start to build detectors to find this radiation and solve the puzzle. The technology was there. It was all there. All people had to do was to put these things together and to make the measurement. People say that maybe it was the fact that the Big Bang theory was started by somebody who had a religious allegiance. Some people think that it was Hubble's embarrassing prediction, which was still showing the universe to have a much lower age. Other people think that this guy Alford, who predicted the radiation, was a Jewish immigrant, and there was some kind of a sentiment of taking those people seriously at that time. Also, people were arguing that there still is no way to make the heavier elements, so how can the Big Bang model be true? And also, making those detectors needed interdisciplinary skills, because making microwave detectors is not something that most physicists learn how to do. And also, people would have to understand nuclear physics, and there weren't too many people with those kinds of skills at that time. People also blamed the Cold War with Russia. In fact, the Big Bang theory had been banned in Russia. It was considered to be Western propaganda and so forth. And finally, at this time, what happened is that there was a new theory that was put forth as an argument against the Big Bang theory, and that is called the steady state model. And I'll talk a little bit about that now. So a physicist, a British physicist, Fred Hoyle, along with Bondi and Gould, proposed a theory where you would be able, you would be able to get the same results of galaxies moving away from each other, which had been shown by Hubble, but you did not need to basically consider that there was any kind of an origin. And the way that he did that was, he said the universe can be expanding, but if there is new matter that gets created in between all the galaxies, then basically no matter how far you go into the past, you still get the same universe. because the density of the universe is the same. And we don't know the size of the universe. That's very, very big, so that doesn't really matter. But basically what you get is the same universe no matter how far in the past you go. So therefore you can get a static, eternal universe and yet have the galaxies moving away from each other. So this was, a new idea, but again, because people did not want to believe in the Big Bang theory, they hung on to it. And in fact, this theory became a huge contender to the Big Bang theory at that particular time. So now the Big Bang theory had to come up with more proofs to figure out, to show people that indeed that was the right theory. And so people tried to do that as well. So in 1952, a guy called Walter Baade actually showed that Edwin Hubble had made a big mistake, that there was not one kind of this variable star, but there were two kinds of variable stars. And if you took that into account, the age of the universe now comes to 3.6 billion years, but that's still very low. Then a few years after that, another guy, Alan Sandage, showed that there was yet more errors in Edwin Hubble's work because he had mistaken some clouds, some very bright clouds in galaxies as stars, and they were actually not stars at all. When he put that factor in, the age of the universe started to become a little bit more respectable, but it was already known at that time that there were stars in the universe that were older than 5.5 billion years. So we still had some ground to cover. So, in fact, the theory that the steady state theory that was put forward gained a little bit more ground when Fred Hoyle and William Fowler found a way to create all the other heavy elements. What they showed was that inside a star, at the very center, the core of the star, you can show that if the star is big enough, that it can actually make in that core, through a process that we now call nuclear fusion, it can make all of these elements. And in fact, this is the only way to make those elements. The Big Bang will never create those elements that we're talking about. So one interesting thing that I'm sure you might have all heard about is that all the atoms that we have in our body, other than hydrogen atoms, all of those atoms have had to be made inside some star. So we are built from the debris of stars in the universe. Some people say we are made of star dust, which is an incredible thing to grapple with. So this thing actually in some ways could have shown the Big Bang theory to be now in better shape, because now we have a way to make the heavy elements and we have a way to make hydrogen and helium, but somehow it did not still take that energy. And so these people said, oh, there must be other ways to build the hydrogen and the helium, but we've already shown that stars can make all these elements, so we really don't need the Big Bang theory at all. Now, another way to try and figure out that the Big Bang theory is correct is to show what the universe looked like in the past. So if the universe is really evolving, if it is changing over time, and if I can show that in the past the universe looked very different, the galaxies were not as developed and so forth, then I could show that the Big Bang theory must be correct. Now that's not very easy to do. Well, first of all, you have to understand that it's actually not so hard to look at the past. On the Earth, we have to dig for fossils to figure out what happened on the Earth, millions of years ago. In space, in the universe, all you have to look is further and further away. The further you look into the universe, the older is what you're looking at, because light from those objects takes time to get to you. So when you see something in space, you're looking at it as it was in the time it took for light to come there. So if you're looking at something that is, let's say, a billion light years away, you're looking at it as it was a billion years ago. So if you can look at things that are far away and things that are close and show that there is an evolutionary history, then you're home. Then you can show that the Big Bang model has to be correct, because the universe is indeed evolving and changing. So that's easier said than done, because at that time, telescopes were not powerful enough to look that far into the past. And if you look only a little bit into the past, then things don't change that much, so you can't show anything. In any case, some evidence did show up in what we call radio galaxies, which are galaxies that emit radio waves. And this man actually showed that if you look further into the past, you find that there are many more radio galaxies than there are near to us, which means in the present universe. And that shows that there is an evolution that is happening. We now know that when galaxies are formed, they emit radio waves, so it makes sense that there would be more radio galaxies long time ago than there are today. In any case, so this was one more little thing, but what we really needed was the smoking gun. What we really needed was the detection of that cosmic radiation that Alford had predicted would come. In fact, Alford's paper that predicted the radiation, the 5-degree radiation, had also been lost in, was buried in all of this. Nobody seemed to care much about it. And so what happened is that these two gentlemen in Princeton rediscovered that whole calculation that Alford had done, and they decided we are going to go look for that radiation. As a matter of fact, on one of the Princeton buildings, they started to build an antenna that they felt would be able to detect the cosmic background radiation. Now the story gets very interesting here. One would have thought that these people put all the hard work, they did the calculation, they would have been able to find this radiation and got the Nobel Prize for it, right? It didn't happen that way. About 50 miles from Princeton is the place where I live, Homedale, New Jersey. And in Homedale, New Jersey, there was an antenna that was being created not to detect the radiation, but to build satellite communication. Bell Labs was into telecommunications. At that time, they were falling behind Russia, which had already launched the Sputnik. And the Sputnik was a satellite, and therefore they were in a position to start satellite communication, and America had fallen behind. And so the government pushed Bell Labs and NASA to do something to catch up with Russia. And as a result of that, they came up with an idea, which it turns out was finally led to the detection of this radiation. I'm now going to give you a little more history about Bell Labs and how this thing happened. So this is the Bell Labs building that I personally worked in for 15 years. I had nothing to do with, building that antenna. That was in the 1960s when I was nowhere in this place. But this is a very remarkable building. In fact, it's a historical landmark because it was the first all-glass building that was ever built in the U.S. It is now historically protected, though Bell Labs, fired and laid off so many people that they had to abandon this building, and it's now been converted into a mall. But this building has lots of history. The first radio astronomy detection happened here. A guy by the name of Karl Jansky was told to build a radio detector so that he could figure out the effect of storms on telecommunications. So, telecommunications was already using radio waves to transmit data and conversations. And they wanted to understand what happens when there is a big storm, how much does it affect that radiation. So this man built it, and he accidentally found out that there were radio waves coming from the center of our galaxy. Nobody had predicted that, nobody knew about it, and it turned out that this is the start of radio astronomy. After this, people found out that there are many, many objects in the universe that emit radio waves. And now radio astronomy has become an incredible way to study the universe and to find new things on it. This was his initial antenna. As you can see, it was sort of, cooked up on the fly. And in fact, there is a little memorial to Karl Jansky on the grounds of the building that I showed you. It's still very much there. People go to visit it. So that was the beginning of radio astronomy. It turned out that Bell Labs at that time did not develop radio astronomy. They could have. They could have gotten Karl Jansky, given him some money, and told him to further develop radio astronomy. They failed to do that, and radio astronomy was developed in academic universities and so forth. So next time, when they built an antenna, so this is the antenna that I'm talking about. It's what they did was they first made a huge balloon. You can see how huge this balloon is. It's 30 meters in diameter. Those are some of the people here. They launched this balloon into space, and they said that we can test satellite communication, even though we don't have the satellites yet, but we can bounce off radio waves from this, microwaves actually it was, from this kind of a balloon, reflective balloon, and we can then build an antenna to detect those waves, and at least we can start practicing what satellite communication would be like. So in order to receive the faint signals that you get from the reflection, they had to build this telescope. This is called the horn antenna. You can see it's quite big. Here are the people standing in there. And this antenna is very sensitive to microwaves. It basically has this shape so that it can diminish the noise that comes from other places, and it can only take the signals that are coming in this particular direction that it's facing. So this was built in Homedale. Like I said, it's 2 miles or 3 miles away from where I live right now. And what happened is that once they were done with this experiment, they had no use for it. Because now there were other better instruments that were being built, real satellites were coming up, and they needed different kind of antennas. And since Bell Labs or people in Bell Labs were kind of feeling guilty that they had let go of one opportunity where they could have become the developer of radio astronomy, they said, we're not going to let go of this possibility. This is an incredible antenna. Let's invite some astronomers to come and do some astronomy here, whatever they want to do. Maybe it'll come and produce some results for Bell Labs. So they hired these 2 gentlemen to just play around with that equipment and whatever they wanted to do. And indeed, they had some ideas about looking at radio waves from the galaxy, and they started to do some experiments with it. In 1964, they had a big problem. They were trying to detect these waves, and there was noise coming that they couldn't get rid of. No matter which way they pointed their thing, that noise was always there. So when they shut the instrument, the noise level was low. The moment they got the instrument open, there would be a huge amount of noise. And they tried everything to get rid of it. In fact, one of the things that they did was there was a lot of pigeons that had made nests inside the antenna. And there was this white dielectric material that you get from pigeon poop. And they tried to clean the whole thing, hoping that that will get rid of the noise. Nothing happened. In fact, the pigeons came back, and they finally had to get rid of the pigeons in a different way. So this is where the story gets interesting. They kept finding out and talking to as many people as they could to find out if there is a way to figure out what this radiation is. Someone said that there are a couple of people in Princeton who may know about what this thing is. Why don't you give them a call? So Arno Penzias, who was the chief person among these, gave a call to Dickey, who was building the antenna. He explained to them what he was observing, and he thought maybe you guys might know what's going on here. And there is a famous phrase that gets quoted in all books on the Big Bang, and that is that when he put the phone down with Arno Penzias, he actually had all of his postdocs sitting out. They were eating lunch together, and he told the postdocs, boys, we have been scooped. What we were trying to do has already been found. So it was disappointing, obviously, for them. As a matter of fact, Arno Penzias and Bob Wilson got the Nobel Prize for this discovery, and unfortunately, the work that Dickey had done never really got recognized. So a little bit of another side story here. So this antenna was actually declared a historical site because of the significance that it has. However, about 2 years ago, Bell Labs, which had now been sold to Nokia, which is a company out of Sweden, I believe, one of the Scandinavian countries, and they decided, in their ignorance, to sell the piece of land on which this antenna is to a condominium developer who was going to dismantle it and build condominiums in its place. And of course, the city didn't seem to care much about it. They didn't know much about what was going on here until a few of the citizens caught wind of this idea and this what was going on, and they decided to take things in their hand, and they said, we can't let this happen. This instrument is too important for the future or future generations for us to let it be destroyed like that. So there was a huge movement that happened. In fact, since I was living in Homedale, I became a part of that movement. And since I knew some astrophysics, I actually went to the city and gave some talks to them to tell them and explain them the significance of what they were going to destroy. We called a whole bunch of journalists in. We got newspaper articles written. We collected a lot of signatures. And the good news is that just about a year ago, they finally agreed that they must save it. They bought the land from the developer, and they have now committed to building an education park and a museum there. And in fact, this picture that you see is the opening ceremony of that park, which happened last year. And it's called the Robert Wilson Park for one of the people that made the detection. Arno Penzias died 2 years ago. but Bob Wilson is still living in Homedale, and he was the person that actually did the opening ceremony of the park. So that's a little side story, and that's how these things happen. So let me tell you now that this particular discovery, first of all, it proved once and for all that the Big Bang theory is correct, because there is no other way in which you can show that such a radiation could be generated other than an explosion that took place that far long ago. There is simply no other way to explain it. And the reason why people are so sure now that this can only be explained that way is because not only do we actually found the radiation at a particular wavelength that they discovered, but we now have measured that wavelength. We've measured the intensity of the radiation at many different wavelengths, and this particular curve that you see is called the blackbody curve, and it can only happen when the radiation is emitted in the way that we explain it to be emitted in the Big Bang. There is no other way to explain the shape of this curve. And you will see that the agreement between experiment and observation, experiment and theory is so accurate. Every little cross falls on this curve, which is actually calculated theoretically from what we know about how these things work. So the agreement between experiment and theory is almost perfect. And with this kind of data, we are now able to do some incredible calculations. Before this, cosmology was an approximate science. As a matter of fact, most academic people will tell their students at that time, don't go into cosmology, it's a dead end. You will never be able to get a career out of it because it's too approximate a science. With this discovery now, we can make such accurate measurements that we can make some incredible predictions. For example, the temperature of this radiation has been measured to 5, 6 significant figures. And as you see, it's not exactly 5 degree K, but it's about half the size, so we now know that's the real temperature. And not only that, using this method, we can actually calculate the age of the universe, and to this incredible accuracy. So cosmology has become now a science that is as exact as any other science that we can do in our laboratories. Even though we have no way to bring the universe into our laboratories, all we can do is make measurements with telescopes, but we can make such incredible measurements. This has completely revolutionized cosmology, and it has allowed us to make and predict measurements and so forth that we could never have dreamed of before. Not only did we measure the spectrum of the radiation, which gave us lots of information, but we also started to get more and more data, and we found out that this radiation is not exactly the same in all directions. In the beginning, when our equipment was not good enough, we thought it was the same no matter which direction you look into. Then we slowly started to figure out, as the time went on and we got better and better satellites to measure this radiation, that there were some differences, and now we have even better measurements and we can show these differences. In fact, we can match these differences now to our universe and show that where you see these green and yellow spots, we have lots more matter, we have galaxies, and where you see these blue and dark blue spots is where we have complete nothing but empty space in the universe. So we can correlate and we can actually show that the formation of galaxies was a result of a certain kind of distribution of the hydrogen gas that happened. And now we, of course, know that this kind of a distribution is the result of what we call dark matter in the universe. Now, in this talk, I don't have time to go into dark matter, but it turns out that you can actually even calculate how much dark matter you need in order to build this kind of a distribution. So this whole thing has led us to incredible amount of information. In fact, one of the things that we also now understand is something called cosmic inflation. We found out that when you look at the cosmic radiation, that there are some things that are not possible to explain. There is something called the uniformity of this radiation, which is very difficult to explain. And there's also something that has to do with flatness of the universe. Again, I won't go into the details here. It turns out that the only way to explain that is something called cosmic inflation, which Alan Guth discovered in 1980. And he showed that the way to make the universe happen and expand in the way it is, you have to have a time period where the universe expands very, very quickly. So this is sort of the rough way. The universe expanded by a trillion times in a trillionth of a trillionth of a trillionth of a second. And that is what we now call the Big Bang. So the Big Bang is now understood to be the cosmic inflation that happened very early in the universe, where there was a huge amount of expansion from a universe that was smaller than an atom to a universe that was about the size of a peach. And then it kept expanding in the way that it's expanding right now. So incredible discoveries were made. The latest discovery we have now found out is that the universe is not only expanding, but the rate of expansion is actually getting higher. This was a contradiction to what was expected, because as people who worked with Einstein's equations had showed that the universe should slow down because of the gravity of all the bodies in it. But instead of slowing down, the universe expansion has been increasing. This is the data for this. And the only way to explain that is yet another mysterious thing called dark energy. So now we know that our universe is actually made up of three kinds of things. Dark energy, which constitutes 70% of the universe. And by the way, energy can be converted into mass with Einstein's equations, so we can actually compare energy with mass. So 70% of the universe is dark energy, about 25% is dark matter, and only about 4 to 5% of it is what we call ordinary matter, which is those 100 atoms that I talked about. The rest of it, we just do not know exactly what it is. But we can do these calculations, which is so amazing, of the percentages that we have. Oops. And I'm coming to sort of the end of the talk here. So this is the latest version of the cosmic background radiation map. You can see the level of detail that we have here, which is amazing in terms of the distribution of the intensity of the radiation over the whole space, the 360 degrees. And from this, we can calculate something called the Hubble constant, which is basically the rate of expansion of the universe today at this point. And this is now become the measure of one of the measures of the universe. So the interesting thing, and this is kind of, I'm going to bring this to a summary here, that what we find out is that we have the universe the way that we have because certain constants in the laws of physics, in the equations that we have, are incredibly fine-tuned for the universe to produce life. Okay? There are 6 cosmological parameters. I've only mentioned a few of them here. And then if you go to the microscopic part, which is the atomic level, there are about 14 parameters which are simply constants. They're called constants of nature. These are constants in the equations, but there is no explanation of why they have the value that they do. As a matter of fact, if we change the value of any of these constants by a small percentage, we can follow what will happen to the universe, and we can show that either the universe will expand so rapidly that there will be no time to form galaxies, or we can show that the universe would collapse so quickly and become a black hole, and there would be no time for life to emerge. And certain other constants will tell you that even if you get a universe where you can build a galaxy and make planets, that there will not be enough time for those planets to build life, because you need a few billion years for life to evolve on any planet, and so forth. So this is something that I am ending my talk with here, because I want to tell you that we don't know everything yet, and maybe never will. But what we also are finding out is that just like religion had these myths that they stuck to, that there are still myths in our science. The myth about eternal universe has finally been broken. Everybody now accepts that we have an origin of the universe, that our universe started 14 billion years ago, 13.8 billion years ago, and that we now understand the whole history of how that happened. But there are other myths that we have that yet have not been explored or broken. So here is one of them that I want to come to. I mentioned those 20 or so parameters, and here I represent them as knobs. Because what I can do is I can take all the laws of physics that I have, and I can, with sort of these knobs are just like a metaphor, an analogy, but I can actually tune the parameters that we put into those equations, and I can show that if I turn any of these knobs by a tiny bit, I get a universe that cannot produce life at all. And so it's a miracle that we have the universe that we do. It looks as if everything was fine-tuned in the beginning in order for the universe to evolve the way it evolved and give us life. So we live in a very finely tuned universe. And you can also see the process of evolution, how it works. And just like in the creation myths, people use these creation stories to tell us something about our life and who we are. Similarly, this science myth, well, not myth now, the science information that we have from the Big Bang Theory, one can apply that to see what does it mean for us human beings. After all, we emerged from that universe that started 14.8 billion years ago. And one of the things that you see is there is always a process of getting together and cooperation. So atoms come together to make stars, stars come together to make galaxies, galaxies then create the heavier elements that can make planets. And then planets have the wherewithal, the medium, the oceans and the water in which molecules can come together to make cells. And then under certain conditions with the right ecology, those cells can come together to make multicellular organisms and so on. So the whole process of evolution is a process of coming together. So where are we today? Is there some place where we need to come together to yet another level? And is that one of the things that the story is telling us? I don't have answers, but I just want to put those questions out there, that with this information now, there are new questions that are being generated that we could never even have asked without this discovery that God made. So here is a little quote from Einstein. Nature only shows us the tail of the lion, but I have no doubt that the lion belongs to it, even though he cannot totally reveal himself all at once. So he's talking about nature and saying that we only see a small part of it, and we're trying to make some conclusions from that, but we don't know what it's all about. And I'm going to end by showing you a picture of my little grandson. I have a grandson born to my daughter just three months ago. And the reason I show you this picture is because I say to myself that things are not great in our universe right now, but maybe not overnight, but maybe in the time that my little grandson grows up, that we would have learned more about the universe and we would have gotten rid of some of the myths that we have, and perhaps we can apply those myths to find ways for humanity to come together in new ways, which is kind of my message today. So here's a picture of my little grandson. His name is Rowan. So thank you very much. Yeah, sure. Go ahead, please. Yes, Bhartendu?
Yeah, two questions. One is, you said that atoms other than hydrogen and helium could not have been formed in the Big Bang.
Yes.
So maybe you can throw some light to
Sure.
why it's so.
Yeah, so it's, yeah, sure, go ahead. Yeah, second question.
I would assume, or I will conjecture that the early universe must have been very, very, very dense.
Very dense.
So why was it not a black hole?
Okay, so I'll answer the second question first because that's an easier one. So in order for a black hole to form, you need two things. You need a lot of density, which we certainly have, but we also need the energy of those molecules not to be as high. So not only did we have high density, we had trillion-degree temperature. That temperature will stop that mass forming a black hole. The reason that black holes are formed in stars is because the stars cool down enough. So if you have a hot star, it cannot form a black hole, and we had a very, very hot Big Bang. So that's the answer to the first question. The second question was about the elements, why the hydrogen and the helium is the only thing that form. That's an interesting thing, because what happens is that the way that elements or new nuclei are formed is that as the universe cools and the energy becomes lower, it becomes possible for neutrons and protons to come together. And they come together from hydrogen, you can start to make helium, right? But now you need the helium nuclei to come together to make oxygen. Then you need the oxygen nuclei to come together to make carbon. By the time this is happening, the universe has cooled down so much that now the energy to bring these things together and make them into new nuclei is not there. So it turns out that you only have a small window, and in that window you're able to make hydrogen and helium and actually a tiny little bit of lithium. And that lithium has also been detected to exactly the amount that was predicted. So this is how great our calculations are. But you can't form heavier elements. The only way you can do that is through stars. And luckily, stars did happen. Yes?
This is not a physics question, it is a philosophical question.
Sure.
You talked about, those knobs, and you said it's in finely tuned
Yeah.
perfection.
Yes.
So where is the room for imperfection, given that all of us who are kind of products of that
Yes.
are imperfect?
Okay, so, I'm talking here about the laws of physics. That is what is fine-tuned. What results from the laws of physics doesn't necessarily have to be perfect. I mean, the laws have to be perfect so that they can produce us. But then that does not imply that we humans have to be perfect, right? That's a completely separate ball game in terms of what we are talking about here. As a matter of fact, our imperfection might be what is needed for something further to happen. And so you could even say that the universe was perfectly tuned to produce imperfect human beings. Right? I want to make sure that I get some students.
Sure.
Yeah,
So, pardon my ignorance, I'm not from the field.
that's okay. Yeah.
This is from popular articles which I have read that the James Webb telescope now can look far back in time.
Yes, true.
And what they are observing is that the structure of the galaxies which
Yeah.
they see far back in time
Yes.
somehow does not conform to the possibilities
Correct.
which are thrown up by Big Bang.
Absolutely.
So, is that a contradiction?
It is not a contradiction. It is a message to us that we need to fine tune and we need to look more into the details of the Big Bang to understand how the galaxies could have been formed so early. Because the prediction of the Big Bang is that it should take more time for galaxies to form. Yet with the Webb telescope, we are seeing that galaxies were formed earlier. So what that means is we have to come up with some other ideas that will show us how those galaxies could form earlier. It does not necessarily mean that there is anything wrong with the Big Bang theory. Now this, by the way, there's a certain amount of sensationalization that happens in the news where people get this kind of a thing and the first thing that they say, oh, the Big Bang theory is wrong. But you have to be careful and look at it, what they're basically trying to get you to read the article. So you have to be very careful when you do that. Yes.
When you talk about something expanding, our general notion is that when it is expanding into something. So when you talk about the expanding universe, what is it expanding into? I cannot grasp this idea.
It's a very, very good question. And if I had more time, I would show you some demos to show you what it really means. Let me put it this way, that the best example of demonstrating this, and it's not a perfectly satisfactory way to do it. The problem, by the way, is that you have to be able to think in 4 dimensions to understand what I'm going to talk about, and even physicists cannot do that. So it's very difficult, but we can simplify the product and show you. So think about a sheet of rubber, right? Think about a sheet of rubber that's expanding. So if the sheet of rubber is expanding into space, then it's perfectly okay, expanding into space, and it makes sense. But what if I say that there is no space around, forget about all the space around, and take that sheet of rubber and wrap it around so that it becomes a balloon? Now, if I blow the balloon, the skin of the balloon is expanding. But what is it expanding into? Itself. You understand? Because, it's again difficult to comprehend because you have to assume that there is no space around the balloon, there is no space inside the balloon, because we are talking about a 2-dimensional universe, not a 3-dimensional universe. So you have to take all of those things out. Only focus on the skin of the balloon. If you focus on the skin of the balloon, you can show that the skin of the balloon can expand into nothing, into itself. And this is what our space is. It's expanding into itself. It doesn't expand. It's not like an explosion of a firework. An explosion of a firework is in space, so things go apart. Here, space itself is created in this process, and it expands into itself. So it's a good question, but there are answers to those questions. You had one, finally. Let me ask. Go ahead.
I was going to ask you about the galaxies.
Okay, so your question was answered? Okay. Yeah, let's have more questions.
Yeah, I was just wondering that, the perennial question of where did it start and where did it end? When you say that, there is a Big Bang,
Yeah.
we always try to put our observations in some context of process. So if you think it from the process perspective, then what started it and where it will end is also something that, it may still be fuzzy, but I think we should have some kind of a direction or few directions to
Yeah.
thinking. So if you can.
So there are directions, but I have to warn you a little bit that there are limitations to science, right? And the limitation is that science will explain how things happen, but it really can't tell you why they happen, because that's not what science does, right? So what we can do is keep going further and further back to understand how something happened. For example, now we actually have a theory that shows what happened before the Big Bang. People used to say, well, what happened before the Big Bang? We have a theory now. We actually know what could have started the Big Bang itself. But you can still ask the question that whatever we are starting with, where did that come from? And so on and so forth. And there is no end to answering and asking those questions.
From a process perspective,
Yeah.
is that construct a good reference frame? Like if it's a process,
Yeah,
then you can,
yeah,
like stars have
yeah.
life.
Life and death,
A lot of processes have
Yeah.
Start and end.
correct.
So is it logical to bring that construct in? Like,
It is logical. It is logical, but we don't always have the answers, right? But your thinking is logical. I mean, right now, in fact, you can predict what will happen to the universe eventually if we make some assumptions about the acceleration of the universe. There is something that says the universe will rip apart and so on. But we don't know enough to be able to make those predictions. In fact, lately, in the last 2 years, we have now found out that some of that acceleration that we were thinking is also slowing down. It's still accelerating right now, but the rate of acceleration is slowing down. So maybe the universe will actually collapse into itself. And if it collapses into itself, then some people have this oscillating universe theory that says the universe keeps expanding and collapsing, expanding and collapsing, which I think actually matches up with some Hindu mythology as well, that says that these cycles keep happening forever and ever. So you're touching on the frontier of science here that we really don't know the answers to what exactly it is. Yes, sir.
Does the Big Bang theory, like the way Wayne said that it started small and then expanded, does it imply that the universe is finite?
Okay, that's the same question that was being asked here about, what is the universe expanding into? So when I talk about that skin of the balloon expanding, the skin of the balloon is finite, right? It is not infinite. So the beauty is that you can actually explain an expanding universe that has no boundaries, and yet it keeps expanding. But it's finite, it's not infinite.
So does it, I think I've read it somewhere, but does it mean that if I go in one direction and begin back?
Absolutely. It will take a very, very long time, but even if you go at the speed of light, if the universe is described by Einstein's equations, then it is absolutely true that if you keep going long enough in the front direction, you will end up where you are. That is what would happen if you do that on the skin of a balloon. So that applies to our universe as well. Anything else? Yeah, sure.
Right. You can see the value of the whole parameters around 70 around. So it is evident that the expansion effect of the universe is visible to us in extremely large scale.
Hmm.
So, as you said that the photons are getting stretched. So
Yes, yes.
how is the photons is getting stretched? Is it the enormous amount of time spent by the photon while traveling to us? Is it because of that? Or
No,
how
it's
is
it's
why the effect is in such a small scale?
the stretching is simply happen. Think of drawing the squiggly line on a balloon. A squiggly line represents a photon, a wave, right? So as the balloon expands, the distance between the two peaks and the troughs of that wave is going to get bigger and bigger. So that means the wavelength is getting bigger and bigger. That is exactly what is happening. And as the universe keeps expanding, it will become bigger and bigger. So these microwaves will become radio waves at some point in time.
Yeah, I'm talking about the scale. Suppose the how can I explain? Suppose I am.
Yeah.
Am I getting stretched by the?
Oh, that's another question. Are you getting stretched? No, you're not. And the reason is that you are in an area where there is so much gravity that the effect of this expansion is literally gone completely. So to look at the expansion, you have to look at the distance between galaxies. If you look at within a galaxy, there's no expansion. And that is because the total effect has to be a result of the contraction effect of gravity and the expansion effect. So inside a galaxy, there is so much gravity that any expansion effect is completely obliterated. But if you go in the space between galaxies where there's not too much matter, then the expansion becomes more dominant and you see the effect of expansion. So yeah, you are not being expanded by the universe at all. Okay, we should end, I think. Yeah.